Okay, this talk will be in English because it's relatively similar to my defense. And that one was also in English. Thank you very much for the introduction. It will be about efficient reconstruction of camera trajectories. Okay, so the technology behind reconstructing camera trajectories from sparse features, as you can see it on the top, is usually structure from motion, and I'll give a short introduction to the topic. So for reconstructing camera trajectories relative to a scene, you usually need a scene, and actually structure from motion comes from image processing, so usually you're just taking some photos of that scene, like this, for example. And at the beginning of the reconstruction, you just have those images, but what you can do is you can detect features in those images, which are here in blue now, and you can detect those features in all of the images, and you can see that they form some tracks now. So in principle, you can connect all the features which belong to the same surface point, and then you have such tracks. Now when you have a look at the first two images, for example, which look like this, and you take the feature matches, so the corresponding features here, and there are closed form algorithms which can directly tell you when you put in 5 such feature matches what the relative orientation of those two cameras is, which looks like this. Now, when you have the relative orientation of those two cameras, it's easy to reconstruct the scene structure, because what you can do is you can just shoot a ray through all those features, and at those places where those rays intersect, you have your scene structure in the end. So, which looks like this. Now, when you have the scene structure, you can easily append additional cameras, because there's another closed form algorithm which is called 3-point algorithm. For that one, you need here 3 features, and on the other end 3 3D points, and then it can align your camera relative to your reconstructed scene points. And this way, with this 3-point algorithm, when you once have the scene structure, you can append additional cameras or additional camera poses to it. Now there's just one problem, and that is that your whole reconstruction was based on 5 or 3 correspondences, so either from the 5-point or the 3-point algorithm. That means that your reconstruction is not consistent. So when you look through one of those cameras, you have a look at those 3D points in red, they don't necessarily match the positions of the detected 2D points in the images. And therefore, there's a technique called bundle adjustment, which tries to move all the cameras and all the 3D points in the scenes so that those errors here between the red and the blue dots shrink. And when you run that, and it looks like this, so you can see all the points move a bit, all the cameras move a bit. When you have a look at the same optimization from the top, then it looks like this, so everything snaps into place, and then you have a consistent reconstruction. Okay, so to recap, the key steps are: at the beginning you have some feature matching and tracking, then afterwards you have those 2 algorithms, 5-point or 3-point algorithm, plus point triangulation to add other cameras, and then to keep everything consistent, you run a path of bundle adjustment. And those bottom 2 steps are usually run in a loop. That means you always add some cameras, then you do bundle adjustment, then you add some more cameras to increase your scene size. This stuff actually works pretty well for individual images, for what it was designed. And the runtime is, or the speed is usually limited by the bundle adjustment itself. And the major problem is that the runtime is proportional to the number of camera poses to the power of 3. That means when you have twice the number of camera poses, then you have 8 times the effort. So it's actually just feasible for about 100 images. And the work I'm going to present you was developed at Disney Research, and they said, okay, that's a little problem. We use such classical structure from motion pipelines for our videos, but we have the little problem that we have high frame rate, so we will have this 100 images within a second, and we have very high resolution, so we have up to 20 megapixels. So we are not talking just about some features, but about tens or hundreds of thousands of features per image, and therefore optimization becomes slow. They said, okay, when we use the standard tools, and we're lucky, we just have a short shot, then we have to wait till the next morning to get our results. But actually what we would like to have for our workflow is something which does this within a coffee break. And that's in principle the topic of this talk. So the question is, what can you do? Well, since the bundle adjustment is the problem, you can optimize there. So you can try to run bundle adjustment with as few data as possible. So for example, trying to reduce the number of cameras you optimize at once, or the number of points you optimize at once. And the other thing is bundle adjustment is an iterative optimization. So that means if you initialize it well, so if your cameras and points are at the beginning already at a nice position, then it doesn't need so many iterations. That means this factor here drops, and you're much faster in reconstruction. Okay, that leads me to this algorithm that I developed, scalable structure for motion on highly redundant data. So large frame rate where all the frames look almost the same, and lots of features in the images, which you don't need all of them. And before I introduce you to the pipeline, the reconstruction pipeline, I would like to show you two building blocks which appear over and over in the reconstruction. The first one is point subsampling, and maybe it's obvious that if you have tens of thousands of features or hundreds of thousands of features, it's not necessary to really use all of them to get a decent result. So actually it turned out that when you just have 60 to 80 features per image, then the results are already nice. And to select or those features you really want to use for optimization, we found that it's a good idea to do a stratified selection in the images. You separate your images, like in those blue lines, and you try in each of those separated areas to get a certain minimum number of features. This ensures that you have a good distribution in the images, and when you select the minimum number of features per stratum, that also makes sure that you have enough constraints per camera. That means that each camera pose is fixed by a sufficiently high number of features or 3D points. And the other thing is, it's a good idea to prefer points which are connected to many cameras. On the one side, this makes sure that you have many constraints for optimization per point when it's connected to many cameras. And the other thing is when a point is seen from many camera poses, then it's very likely that this point is not an outlier. Now, when we have a look at the results, so here that's a measure of the camera drift. So in principle, how far off the camera is from the position it should actually be. On different scenes at the bottom, and we did this reconstruction once for using all the points from all the features in the scene, and once by a subsampled set, which has about 60 to 100 features or 3D points per image. And you can see that the results approximately stay the same. So sometimes the subsampled reconstruction is a bit better, so lower numbers. Sometimes the reconstruction with all of the points is a bit better, but the order of magnitude of the error is approximately the same. When you have a look at the timings, then you can see that using the subsampled point set increases the reconstruction speed by a factor of 3 in most cases. Okay, the other building block is about the cameras. Maybe you remember there was this relationship, bundle adjustment runtime to camera poses to the power of 3. So if you could reduce the number of camera poses you have to reconstruct, it would be very beneficial. So the idea is, why not reconstruct just parts of the scene? So for example, in the example on the right, just reconstruct those 3 cameras which are connected by such blue triangles at once. And then you have many small partial reconstructions. And then it would be nice to have a magical algorithm which joins all those partial reconstructions to one global reconstruction, and luckily there is such an algorithm which is cited at the bottom here below. So it really works like that. You hand in the relative camera poses for overlapping triplets of camera poses. So in principle, in those triplets, the cameras have to be shared. And the output would be globally consistent camera poses all together over your whole scene. And the nice thing from this technique is that it's actually without considering 3D points. So once you have the camera poses found out by bundle adjustment, it just operates on the camera poses. So there's by far less data to concern. And the other thing is that the whole optimization in this case is a linear method. It means it's not iterative, it's just inverting a matrix. Therefore, it's much faster than bundle adjustment could ever be. Okay, so having those two building blocks, the point subsampling and this linear camera pose estimation, let's have a look at the reconstruction pipeline. The beginning is relatively similar to what we saw in the classic way. So we have our images, we do feature detection and tracking. Then we have our tracks, our feature tracks, so we know how points move on the images. And starting from there, we do interleaved window bundle adjustment. It means we're going along our video stream in a sliding window, and we overlapping sliding windows, and we just have a look, or we just reconstruct with bundle adjustment what's inside of this window. We don't reconstruct the whole scene. So let's have a look at that. Yeah, it's called Interleaved window bundle adjustment. That means even in this window, we are not using all the camera poses, but just some of them. Okay, so here we have such a window. Camera is moving forward, so from left to the right. And there are the key steps, which are at the beginning, you always want to add the next keyframe to the window for your optimization. Then you might want to remove some old keyframes, which are no more necessary in this window. And the last step is then the actual bundle adjustment to find out the correct camera poses in this window. So for adding a new keyframe to the window, we always assume that we have already reconstructed an older window. So in principle, the solid cameras here are the ones from which we know the poses, the keyframes, and the other ones are just skipped. And now the question is, what is the next frame to add to this reconstruction? And actually, we're just trying out some of the frames. And for every of those frames we try out, we try to answer the question, is this frame stably connected to the rest of the window? So we really just try out reconstruction, finding this frame's pose, and if it works well, then we say, okay, it's stable, and if it doesn't work well, then we don't use it. And in the end, we in principle select the furthest frame, so the one which is most away from the previous window, which is still stably connected, which might be this one, for example. Then at the other end of the window, we ask the question for each of the keyframes which are still in, if this keyframe is still necessary to reconstruct the other end of the window. And if it's necessary, we keep it. If it's not necessary, like for example the last one, then we just drop it. That means that we have a window which grows at the front and drops camera poses in the end. And on this window now we do this interleaved bundle adjustment. And interleaved means we want to save compute time. We're not optimizing on all of the camera poses. We just optimize on a subset like this. So close to our new camera on the right, we want to have more camera poses to optimize, to have more constraints. To the other end of the window, we want to have larger distances. And then we run the bundle adjustment on those cameras. So they change a little bit in pose. Now the question is how to get the other camera poses consistent with these optimized poses. And therefore what we do is for those changed camera poses which were optimized with bundle adjustment, for them we keep those relative pose constraints from this linear camera pose estimation technique. So in principle for all possible triplets among those cameras, we share the relative poses and we just put those relative poses to a database. And from previous windows, where other cameras were selected for bundle adjustment, there we can, in principle, recover those linear pose constraints and use them to realign the poses of the not optimized cameras and put them to the right position. That means we just have a fraction of the effort for bundle adjustment, but anyway have a consistent reconstruction of our camera trajectory. Okay, let's go back to the pipeline. So the results from this step are so the important results are on the right, the arrow, the camera pose constraints. So actually from this interleaved window bundle adjustment, we just remember for triplets of cameras the relative pose and everything else we throw away. Then the next step here in this pipeline is global anchor constraints, which is actually loop closing. So in this step, we consider if a camera returns to a position where it has been before, then we would like to connect those camera trajectory paths. From this step, from those global anchor constraints, we also just store those relative camera pose constraints. So in principle, we just store how a camera pose from the one end of the loop is oriented relative to the other end of the loop. And then in the end, we have two bunches of camera pose constraints. One set which tells us how the cameras along the video, so from one frame to the next, are aligned relative to each other. The other bunch tells us how the ends of loops which were closed are aligned to each other. We put all those constraints in our linear solver, which is actually pretty fast, and get a good global initialization for every camera pose in the end. And finally, we just have to run one final pass of bundle adjustment to refine the result. And this final pass is already very well initialized by this linear technique before, and we have our results. Okay, let's have a look at some results. So what we did, since we didn't have a high-end camera which could take 120 frames per second, 20 megapixels, we had a look at the Stanford Light Field Archive. They take 10 megapixel images and they take it aligned like you see in the video. So in principle, those sets here have about 300 images. And we tried to reconstruct the camera poses from here. If you use a standard tool like Visual SFM, which is free and everybody can download, you would have to estimate about 50 minutes of reconstruction time. And with this technique, you can see that we reconstruct all of those scenes with 300 images below 35 seconds. So it's really within the coffee break. So that's different scenes. You can see that in blue, that's in principle the linear reconstruction, so the sliding window along the camera stream. And in red, that's the final bundle adjustment, which optimizes in the end. And in between, what you cannot see is in principle this linear pose estimation technique, which optimizes all cameras. Yeah. Okay, yeah, the results look like this. So you can see in principle all the camera poses were nicely detected at the correct position in the grid. So it's actually pretty precise. And also the scene structure is reconstructed relatively well. Okay, we did another test to see how well it works with really lots of frames. So we did a cooperative capturing session of an office. We took full HD videos from 3 different cameras, 14,000 frames or about 6 minutes of footage in general. If you would use a standard tool for that one, you would have to estimate some months of reconstruction time. So the videos actually look like this. So we just moved around with some cameras. You can see on the chart on the right that our reconstruction time was below half an hour. So you again have in blue the linear reconstruction, then in orange, that's this loop closing anchor constraint thing where we try to connect the different video streams. And you can see for such enormous numbers of frames, it's really this linear method which takes the most time. So that's in principle the largest block over there. So estimating the raw pose of every camera consistently to all others is what takes the most time, and then the final bundle adjustment is relatively short in the end. Okay, and this reconstruction in the end looked like this. So you can see all those smooth camera trajectories. From the spacing of the cameras, you can see a little bit the different frame rates of the cams. You can see that they cooperatively reconstructed the same surrounding structure. Yeah, there's some compression artifacts, I think, from the system here. Yeah, but that's what it looks like. We also did quality evaluation. So we rendered a small scene from the Open Movie Project Sintel, where we knew the ground truth camera trajectory, and then we compared our reconstructed camera trajectories to the ground truth. Here at the bottom, you can see the standard deviation, so in principle, the offset from the ground truth. So lower numbers are better, and since this is a logarithmic scale, you can see that we are usually about an order of magnitude better than other techniques. So like PTAM or this Visual SFM I mentioned before. Okay, and we also did the timing evaluation against some other techniques. So the first two, the ones in the greenish colors, are really techniques which were made for images, and you can see that the runtimes explode when you use, let's say, more than 100 or 50 frames. And the gray techniques are actually really for video camera tracking, so the Voodoo camera tracker or LSD Slam, which is really actually a real-time method to reconstruct camera poses. And you can see that we're actually per frame faster than all of the others. And when we really just consider the structure for motion part, so without extracting the features from the image, which can't be accelerated that much, then we're even about 6 times faster. So that's just the little thin red bars, and we're even 6 times faster than this real-time LSD Slam method for reconstruction. Okay, that's all for my talk. I'd be glad to answer some questions if there's time. Otherwise, thanks for listening.
Thank you very much.